Hey guys, welcome to Science Help's first chemistry video. So our first video here will be talking about quantum numbers and periodicity. So quantum numbers and periodicity, I chose to review these because it's pretty basic, but at the same time it's also important in getting kind of what other topics that we'll be discussing and more complex topics within chemistry. So it's important to have a good base in these topics before you really try and master some more complex topics. So we're going to be talking about first quantum numbers, and in our world we're going to be talking about 4 different quantum numbers. The first one of these is the principal quantum number. I'm just going to write quantum number like that in order to make it a little bit simpler for us. And basically what the principal quantum number is describing is the average distance of an electron from the nucleus in the atom. So basically you have all these electrons in this electron cloud moving extremely rapidly, but these quantum numbers are trying to describe the nature of a specific electron within that atom. And usually, if you're given any type of problem, it'll say something along the lines of what is the quantum numbers of the highest energy electron, which is just the valence, the last valence electron of that atom. So the principal quantum number is describing the average distance of the electron from the nucleus, which we can also describe as simply the shell that the electron is in. And it is denoted by the variable n. So these values can range from 1 through 7 because that is how many shells we have. And basically all it is it's just what row the element can be found in the periodic table. So the principal quantum number is basically the simplest quantum number out of the 4. The next one is the angular momentum quantum number. And what that's describing is the shape of the orbital that this electron exists in, and is denoted by a L, and the values that we'll be dealing with are 0 through 3. And if you've done any type of electron configurations, then it'll really help to connect these angular momentum quantum numbers with the different levels of kind of subshells. So 0 corresponds with S, 1 with P, 2 with D, and 3 with F. So just kind of looking at an element on the periodic table once again helps us quickly denote where what angular momentum quantum number it has. And then the third one is the magnetic quantum number. And what the magnetic quantum number is describing is the orientation of the orbital in space. So basically where in the atom this orbital is in relation to the orbitals that are around it. And it's denoted by an M sub L, and its value ranges from negative L to positive L. So before you really figure out what value that holds, you need to first figure out the angular momentum quantum number because it is dependent on that. The final quantum number that we'll be talking about is the spin. and that is denoted by m sub s. It's technically magnetic spin, but you can just shorten that down to spin, and it has two values always. It'll have one of two values. It's either positive 1/2 or negative 1/2. And all that means is, does the electron have a positive spin or a negative spin? And this is where you'll get the Pauli exclusion principle. And what the Pauli exclusion principle says is that no two electrons in an atom can have the same exact quantum numbers. So two electrons can be in the same shell, they can have the same, the orbitals can have the same shape, they can have the exact same orientation, but, and basically if they share these three numbers, that means that they're going to be right next to each other. So if that happens, then they cannot have the same spin. They must be spinning in opposite directions, one positively and one negatively. And that's basically what the Pauli exclusion principle says here. So you can't have two electrons with the same exact 4 quantum numbers. So in order to show this a little more clearly, we're going to do an example here. And so we can just kind of arbitrarily pick an element here. So here we can just do tin. So looking at the periodic table, you can see that tin is in the 5th row of the periodic table, so that gives us a principal quantum number of 5. And obviously we're doing the highest energy electron in a tin atom. So, and then before we proceed any further, let's get the electron configuration down, because that'll actually help you kind of see where these numbers are coming from. So the electron configuration for tin, using kind of like the, I mean, I won't call it a cheating method, but whatever you want to call it whenever you use the most recent noble gas to kind of shorten it down. And then you got 4d10, 5s2, and then p3. So now we're talking about the magnetic quantum number. So as you can see simply from this right here, the last electron falls in the p orbital. So, so as we can see from our other sheet, the p orbital is given the magnetic quantum number 1. So now we move, the angular momentum quantum number. So now we move to the magnetic quantum number, and basing it off our angular momentum quantum number is either going to have a value of -1, 0, or 1. And sorry, I just caught a little mistake I made up here. It's P2 because it is the second, it is in the second column of the P elements. So here, and because there's only 2, and the P orbital can hold 3 electrons, all you have to do is basically count 1, 2, and then you know it's 0. And this will work for anywhere. All you have to do is figure out what the angular momentum quantum number is, so you know your possibility of magnetic quantum numbers, and then just figure out how many valence electrons it has within that P, D, F, whatever it may be, within that, and then basically just count down to figure out what its magnetic quantum number is. And then finally, we have our spin quantum number. And because there's 2, we get a positive value of 1/2. And you may be tempted to say -1/2 because you get one filling up positively and then one immediately pairing down negatively. But that's where we get that's where Hund's rule comes into play. And what Hund's rule says is that when an electron is added to a subshell, it will always occupy an empty orbital if one is available. So the P category of orbitals has 3 empty slots. So 1, 2, 3. So, and then the S has 1. So tin has 4 valence electrons. So the first 2 are going to fill up the S right there. But then the next 2, one is going to go right there, up, because we always go up first. And then while we might be tempted to put one down right next to it, we're just going to put the next one up. So here, and because we always put positive first, that's where we get our +1/2 from. Alright, so next we're going to move on to periodicity, which in my opinion is probably more important than quantum numbers because they're applicable in a wider range of settings. So here we're going to be focusing on periodic trends. And we're going to be focusing on 3 different major periodic trends. The first one of those is atomic radius. And the second one of those is ionization energy. So I don't know why I said that so weirdly. Ionization energy. And then the third, and without a doubt the most significant, is electronegativity. It is the longest and it is the most important out of these 3. So in order to help you kind of memorize this, I'm pretty sure Mr. Thread, that's probably where I picked it up from, but it really is the most effective way of memorizing it. You just put an R down in that corner for atomic radius, and then you put an I and an E in this corner, and basically wherever that letter is basically where that periodic trend is going to be highest. So in this corner, atomic radius is going to be highest, which means as you go down, atomic radius is going to increase, and as you go left, it's going to increase, and then it'll decrease going up and then to the right. And the reason why that is because as you go down, you're adding more shells, which are farther away from the nucleus, so obviously the radius is going to be higher. And as you go to the right, you're keeping the electrons in the same shell, but you're increasing the number of protons, so they're kind of pulled in tighter, which is why the atomic radius decreases going to the right, and then increases going down. And then ionization energy is how much energy it takes to take away an electron from the nucleus of an atom. So, and that is, it increases as you go to the right, and then it also increases as you go up the periodic table. And as you go to the right, and the reason why this is because as you go to the right, protons are added to the nucleus, which increases its positive charge. So the negatively charged electrons are going to be more attracted to the nucleus because of the greater positive charge. And then, and then moving down the periodic table, ionization energy decreases. And the reason for that is because as the shells are added, they're farther away from the nucleus, so they're easier to take away. So really the reason why ionization energy is on the opposite corner as radius is really for the exact same reason, just applied in the opposite way. And then most importantly is electronegativity, which also increases to the right and increases as you go up. And electronegativity is just a way to describe how strongly the nucleus of a atom wants electrons, how strong its attraction is. And it's similar to ionization energy, where because right here you have the smaller atomic radius, the nucleus is closer to electrons of other atoms, so it can attract them more easily. But electronegativity is definitely the most important one to really grasp a hold of, because whenever we're talking about types of bonds, and especially on the AP and IB test, whenever you have to describe why bonds form and how bonds form, electronegativity is going to be crucial in that, because it's all about how the nucleus attracts atoms. Alright guys, well that's all for this week's video. If you have any questions or any suggestions for what next week's video should be over, please send us suggestions at sciencehelp@gmail.com. So if you have any questions over this video, or if you have trouble with a certain topic, or you guys just started studying something and you want us to cover it, and if you want us to cover specific things within that topic, please just send us an email at sciencehelp14@gmail.com. That's sciencehelp14@gmail.com. Thank you, and see you guys next week.